Today we will continue our discussion on error analysis. Let us recap what we have seen in error analysis. Whenever we take a measurement, we have seen that precise measurement we may not know the exact value, and therefore, there is always an error in the measurement which we take, and we want to quantify that error. We want to have an estimate of how much that error is. So, in case if we do not have the precise measurement known to us, then one of the ways we do is we take many readings of the same measurement and we obtain a mean value, which, as we have seen, is equal to sum of the individual values divided by the total number of observations. Based on this, for each of these observations, we define an absolute error, and when we do this, we assume that the mean value is the precise measurement. So, for example, in reading 1, the absolute error will be A1, the reading minus the mean, the absolute value of that, which means whether it is plus or minus, we take it as plus. So, then we can define for each of these measurements, we can find the absolute error, and we can take the mean of all absolute errors, which we call as delta A mean, and that, as we have seen, is given by sum of all the absolute errors divided by the number of observations. And once we have obtained this, then we can say that the measurement which we will take, it will lie between A and A minus delta A mean and A and A plus delta A mean, which means delta A mean, which is the mean absolute error, that gives us the range in which we can expect the measurement to lie. Based on this, we define a relative error, which is equal to delta A mean divided by the mean. That means, we divided by the quantity error by the quantity which we are measuring, and this will be a fraction, and the relative error can often is expressed as a percentage, and which we call as the percentage error, and the symbol sometimes uses delta as in the small Greek alphabet, and that is delta A mean divided by A mean multiplied by 100, that is what the percentage would be. Now, let us see how errors are combined, and we need this. For example, we have a quantity which is obtained as a sum of two quantities or as a product or division of two quantities. That means, to find, let us say we want to find the volume flow rate of certain amount of fluid which has flown. So, that will be equal to volume divided by T. Now, when we measure the volume, there will be some error associated with the measurement of volume. Similarly, when we measure time, there will be some error associated with measurement of time. So, now what we want to know is, when we measure the flow rate using this formula, when we write it, we do not measure the flow rate directly, we use the formula to calculate the flow rate, then how much is the error in the flow rate. We know the error in the volume, we know the error in time. From this, how do we estimate the error in the flow rate? And for this, we realize the formulas we have, typically we can divide them into two categories. So, let us see how errors can be combined, and how do we find an error in a quantity which is obtained as a combination of different measurements. So, we will look at combination of errors, and here, so first we will look at quantities which are obtained as a sum or difference. So, suppose we have a quantity A which is given as A plus minus delta A. Here delta A is the error in A. Then we have a second quantity B which is given as B plus minus delta B, where delta B is the error in B. And we want to, there is a quantity Z which is equal to A plus B, the sum of A and B, and we want to find the error in Z given the error in A and the error in B. So, Then what we do is, the error in z, we can write it as z plus minus delta z, and this will be equal to a, which will be a plus minus delta a, plus b, which is b plus minus delta b. So, this if we expand, this will be equal to a plus b plus delta a plus minus delta b. So, when we take this sum of errors, now the error could be on either side. So, whenever we have a plus minus sign in the error, we take it as additive. We never take it as subtractive, because we want to look for the maximum error. So, here because z is equal to a plus b, we cancel this on both sides, and what we get is delta z is equal to delta a plus delta b. So, when we sum up two quantities, the error will be summed up, and that will be the error of the sum quantity. Similarly, let us look at the subtraction, and this is where we will have to be slightly careful, because suppose z is equal to a minus b. Then if we use the same thing as we have done before, z plus minus delta z, this will be equal to a plus minus delta a minus b plus minus delta b, and this will be equal to a minus b plus minus delta a, and once again we will get plus minus delta b. And so, now if we are looking for the maximum error, what we will get is this, the maximum error here will be given by, so we have plus minus delta a plus minus delta b, and if we look for the maximum error here, then it will be clear the maximum will be whatever is the biggest number which can come from here. So, that will be delta a plus delta b. So, therefore, even when we subtract, so if z is equal to a minus b, then delta z will be equal to delta a plus delta b. So, errors, even though in the original quantity the things are subtracted, but when we add the errors are added. And this you can also look at, that the error, we are taking the absolute errors, and when we take absolute, negative becomes positive. So, therefore, this is another way of seeing why these are added up. Next comes when we have a product or a quotient, which means we have a quantity z which is equal to a divided by b or a multiplied by b. Let us first look at the product. So, if z is equal to a times b, then we use the same thing again, z plus minus delta z is equal to a plus minus delta a times b plus minus delta b. And now, when we expand this, this will become equal to a b, and then we have plus minus delta a times b plus minus delta b times a plus minus delta a delta b. And here what we do is we divide everything by z. When we divide by z, we divide the whole expression by z. So, when we do that, what we will get is 1 plus minus delta z by z. This will be equal to, so let us just bring this page again, and we have this here, we will keep on copying from here. This will be equal to, now a b divided by z is a b, so this will become 1 plus delta a by a plus minus delta b by b, and then we have plus minus delta a delta b divided by a b. So, now here once again what we will do is the plus minus will be replaced by plus, because we are looking for the maximum error, And the second thing which we do is that delta A delta B, this product we will neglect, because it is expected that the error will be small as compared to the original quantity, and there is a product of two small quantities. So, because it is a product of two small quantities, this is neglected. So, therefore, what we get is the error delta Z upon Z is equal to delta A upon A plus delta B upon B. So, this is how we obtain an error for products. So, if the product quantity divided by the original quantity is equal to sum of the relative errors here. And for those of you who understand logs and differentiation, you will see that this formula can also be obtained by taking logs on both sides and performing a differentiation. But that we will leave, because for now. And similarly, if Z is equal to A divided by B, then once again we will get this formula for the relative error, that delta Z upon Z, this will be equal to delta A upon A plus delta B upon B. So, once again the relative errors of the two quantities will be added. Now, we can extend the formula. Suppose if Z is equal to A to the power of n divided by B to the power of m. Now, for A to the power of n, we can take repeated multiples of A. Similarly, for B to the power of m, we can take repeated multiples of B. And from here what you will realize is that delta Z upon Z, this error will be equal to n times delta A upon A plus m times delta B upon B. So, the power which is there comes in as a multiplicative factor in front of the individual error. Now, this also tells us that whichever term has the biggest power, that term can be the source of biggest error. So, we have to be more precise when we measure that quantity, so that the error associated, if delta A by A is less, even if n is large, the total contribution to the error will be less. Now, this formula which we have, delta Z by Z is equal to plus minus n delta A by A plus m delta B by B, will also work for the percentage error, and we can, because in both sides when we multiply by 100, we will get the same thing. So, we will say percentage error in Z is equal to n times percentage error in A plus m times percentage error in B. So, these are the formulas we will use when we have to find the errors of products and divisions. And let us take a small example. The heat generated in a wire where the current of I amperes is flowing and whose resistance is R is given by I square R times T. Power is equal to I square R, and when we multiply it by T, that gives us the total heat. So, here I is the current, R is the resistance, T is the time, and H is the heat generated. So, here now if we want to find out the error, if it is given to us that error in measurement of I, R and T are 2%, 3% and 1%. Relative errors in measurement of I, R and T are given to us, and we want to find the relative error in the measurement of the heat generated. So, then we will go by the formula delta H by H is equal to, now this I square. So, it will be 2 times delta I by I plus delta R by R plus delta T by T and if we express each of them as a percentage. So, because they are given as percentage, so what we will have is delta H by H in terms of into 100, and that is what will give it this in percentage will be 2 delta I by I into 100% plus delta R by R into 100% plus delta T by T into 100%. Now, these are given to us. So, this will be equal to 2 multiplied by 2% plus 3% plus 1%. So, this total will be equal to 8%. So, that means the error, if we put in delta H, this will be equal to in percentage, this will be equal to plus minus 8%. So, and as if it is required, then this 8% can be converted back into the units of delta H if we know the value of H, and we will see a similar example towards the end of this topic. Now, having seen this concept of errors, what we have seen is how do we find errors in quantities which are added and errors in quantities which are either multiplied or divided. Next, we talk about significant figures in a measurement. Whenever any measurement is reported, then in the measurement we have the uncertainty in the measurement is in the last digit. The last digit could be either maybe less or bigger by an amount of unity, and this is what we account for all this through significant figures. For example, when we say the time period of a particular pendulum is 1.62 seconds, then here we know 1 and 6 are reliable digits, whereas when we say 2, this 2 could be the one where there could be a possibility or uncertainty is in the digit 2. It could be either 1 or 3 or a fraction somewhere lying between 1 and 3. So, this is where the uncertainty comes. So, now when we talk of 1.62 seconds, we say this measurement 1.62 seconds, we say this is correct up to 3 significant digits. So, in a digit which a measurement like 1.62, this has got 3 significant digits. We take another measurement, take an example, suppose we have 20 as 287.5 centimeters. So, this means we are taking our measurement with a ruler which has 1 millimeter graduation, we are going up to 1 millimeter. So, here we have 4 significant digits, and always the uncertainty is in the last digit. Now, the significant digits indicate the precision of an instrument which depends on the least count. Now, what we should also realize is that the choice of different units should not affect the number of significant digits. And the reason for this is that the least count of the instrument will not change whether we change the units from centimeters to millimeters, it will be the same. And so, for example, when I have a measurement of 2.308 centimeters, this has got 4 significant digits. Now, if I look at it, this measurement in millimeters, it will be 23.08 millimeters, and once again this will have 4 significant digits. If I put this, look at this in terms of meters, this will be equal to 0.02308 meters, and number of significant digits in all of these should stay to be 4. And therefore, keeping this in mind, we have certain rules for determining the number of significant digits. The first rule is that all non-zero digits are significant. So, wherever there is a non-zero digit when we see a measurement, that has to be counted as a significant digit. The second rule is the zeros which come between two non-zero digits are significant irrespective of the decimal point. And for example, in this example above here, when I look at 23.08, there is a 0 which comes just after the decimal place, but then still this 0 will be counted when we count in significant digits, because it is surrounded by 2 non-significant digits. So, when we write 23.08, we will talk of this as 4 significant digits. Now, the third rule, these were sort of simple rules, now we have to be a bit careful. If a number is less than 1, that means the number will be something like, if we express it in a decimal, it will be 0 point something. Now, there, if that is so, then zeros to the right of the decimal point, but to the left of first non-zero digit are not significant. And let me give you an example of this. For example, when we say 0.00238, then we observe that we are starting with a number, the decimal, the full part here is 0, this number is less than 1, then there are 2 zeros after the decimal point, these will not be significant. So, in this number we will have 3 significant digits. So, this was the third rule. Now, the fourth rule is, if there is a full number, that means there is no decimal point, then in this number, if it ends with zeros, the trailing zeros are usually not significant unless if the measurement has been taken up to that accuracy, which means, suppose if we have a measurement of 123 meters, this has got 3 significant digits. We convert this into centimeters. So, the same measurement will become 12300 centimeters, and here the last 2 digits, these 2 zeros, they will not be counted in the significant digits. and the number of significant digits will be just 3 as before. Now, the final rule which we have here is, if there is a number with decimal point, let us say for example, we write a number 3.500, we write it like this. Now, here because the 2 zeros have been included after the decimal digit, that means the measurements were accurate up till this unit. So, therefore, in this case the number of significant digits is equal to 4. So, the zeros, the trailing zeros in numbers with decimal points are significant. And sometimes to get rid of this confusion, the number is reported in a scientific notation. So, we report the number in scientific notation, which means the number is written in powers of 10. So, any number is expressed as a into 10 to the power of b, where a is between 1 and 10. So, a will be a number between 1 and 10, and b is the exponent, and b could be positive or negative. If the number is less than 1, then b will be negative, otherwise it will be positive. So, b is an exponent, and then whatever is the number of significant digits in a will be the number of significant digits in that number. So, this way then the ambiguity is resolved. Then we also define something called, if we want to work out what we call as the order of magnitude, where we want to have an estimate of the measurement, not the precise value, but how much it is. For example, when we have something like 1 meter or 2 meters length, we call them as the order of magnitude of 1 meter. But if something is 100 meters or 110 meters, then we will say the order of magnitude is 100 meters. So, the order of magnitude, how we write is, again if we express the number in scientific notation, then we will write it as a multiplied by 10 to the power of b, and if a lies between 1 and 5, then we say the order of magnitude is equal to 10 to the power of b, or rather we call, एक मिनट इसको last part change करना है. I will start from order of magnitude, ये a into 10, यहाँ तक तो ठीक है, इसके बाद चेंज करना. ये ऑर्डर ऑफ मैग्नीट्यूड से दोबारा ले लेता हूँ. ओके, कंटिन्यू करते हैं. सो नेक्स्ट वी टॉक ऑफ order of magnitude. Now, if a quantity is written as, in the scientific notation, as a into 10 to the power of b, then if a lies between 1 and 5, then we round it off to 1, and then we say the quantity, we make an estimate of this as 10 to the power of b, and b is called the order of magnitude of the quantity. And if a lies between 5 and 10, then we round off to the next digit, which means we call it as 10 to the power of b plus 1, and in this case b plus 1 is called the order of magnitude. Order of magnitudes are normally used to make rough estimates of the quantities, and they will not be very exact when we talk of order of magnitude, but this is to give an idea of how much is the sense of measurement. For example, if something is 1.28 into 10 to the power of 7 meters, then we say the order of magnitude of this length is 10 to the power of 7 meters. And similarly, if I talk of the diameter of hydrogen atom, then we observe the diameter of the hydrogen atom is 1.06 into 10 to the power of minus 10 meters, and then we say its order of magnitude is 10 to the power of minus 10 meters. So, this is how we work out. Now, in certain quantities, what we find is that there are in some formulas there are some constants. For example, let us look at a very simple formula. Diameter is equal to 2 multiplied by radius. Now, in this particular formula, 2 is a number which is exact, and so this has got infinite significant digits. So, we do not, that means we are assuming, or not, in this case the number is exact, so there is no error in this number. Similarly, for example, when we calculate the circumference, we have 2 pi r, and the number pi can be calculated to as many significant digits as we like. We can read the formula. So, therefore, when constants like these come in formulas, we do not take any error associated with them, they are assumed to be exact. Now, we will like to see another important aspect of these things, and which is the rules for operations when we have quantities with errors in them. And the basic rule which we have is that the final result cannot be more accurate than the original measured values. So, when we calculate a quantity, then we will look at the least accurate value from these measurements, and whatever is the order of magnitude of the least accurate measurement, that will be taken as the order of magnitude for the final quantity. So, for example, let us see, we have density is equal to mass upon volume, and let us say mass of a quantity is given to us as 4.237 grams and the volume is given as 2.51 centimeter cube, and we are to calculate the density of this. Now, today this is an era of calculators. If I ask anyone to do this, you will take a calculator, you will punch these two numbers, and when you calculate the density using these two numbers, the calculator will give you an answer something like 1.688, I am copying this, 04780,876, depending on how many digits are there in your calculator. Now, you can understand, when I write an answer like this, this gives a sense that the quantity is accurate up till this last digit, which is 0.000000 up till whatever the number here is, whereas our original measurements are correct in the first case up till 4 significant digits or 0.001 grams, and in volume up till 0.01 centimeter cube or 3 significant digits. So, then expressing my answer in terms of these 11 numbers after the decimal is an absurd thing to do and is wrong. So, therefore, how do we work out when we have operations like this? Then how should we calculate up till which digit should we write the final answer is the question. And let us try to understand this very well, because this is something we have to be very careful about. So, let us see how many digits should we carry around when we have multiplication or division, and then we will see for addition and subtraction. Now, for multiplication and division, the rule is that the final result should retain as many significant figures as are there in the original number with least significant digits. What this means is, you are multiplying or dividing, or the formula contains all this of quantities or 3 or 4 quantities. First quantity has 5 significant digits, second has 6, third has 3 and fourth has 1. So, then the final result which you have should contain as many significant figures as the one with least significant digits. So, in this case which I said, if we had 1 significant digit in these 4 quantities, then final answer has to be with 1 significant digit. And let us go back to our previous example, where we said that the mass was 4.237 grams and the volume was 2.51 centimeter cube, and we wanted to find the density. So, we see in this quantity, in mass there are 4 significant digits, in volume there are 3 significant digits. So, finally, in density we will carry only 3 significant digits. So, when we look at the answer which we had, for the density, when we used the calculator, we got an answer of 1.688 such a number. Now, we have to write this answer only up to 3 significant digits. So, that means we will go up till 1.688. Now, the digit after 8 is greater than 5, that means we will have to round up our answer, and so if the answer has to be expressed in terms of 3 significant digits, so the density will be given as 1.69 grams per centimeter cube. I will talk a bit about this rounding after I talk about addition and subtraction. I will give you the rules of rounding also. But secondly, let us take the case of addition or subtraction. Now, it is very clear in addition or subtraction, when we are adding 2 quantities or subtracting 2 quantities, then these 2 quantities have to have the same dimensions. They cannot be 2 different dimensional quantities. For example, we can add 2 lengths or we can add 2 masses, but I cannot add a mass to a length. So, now here what we have to go is, how much is the error in each of these quantities, and whichever quantity, if I am adding up 2 quantities, whichever has the most error, that is the error which I will have to take. So, here what we do is, we retain in the final result, when we add or subtract, we retain as many decimal places as are there in the number with least decimal places. And it becomes clear with an example. Suppose I am adding up 3 masses there is a mass 436.32 grams, there is another mass 227.2 grams, and then there is 0.301 grams. If I have to add up these three masses, then if we total them up, this comes out to be 663.821 grams. Now, we look at each of these individual masses, we find the second mass has got only up to 1 decimal place. That means, we will finally have to write our answer correct up to the first decimal place. So, this answer should be reported as 663.8 grams. Because in this second digit, it could be 0.21 or 0.22 or 0.23. So, adding something about which we are not sure will not make any sense. So, that is why we have to do it like this. Now, here implicitly I have used the concept of rounding off, which you must be familiar with, but let us just formally see this also. And rounding off means these are very obvious rules. For example, let us say we have a digit 2.746 and we want to write it up to 3 significant figures. You calculate a number, you get this, and you want to now write it up to 3 significant figures. 3 significant figures means we have to go up till this digit. So, now your common sense tells you, you can either put it as 2.74 or 2.75, but because this digit is bigger than half, you will round it up as 2.75. Similarly, if you have a number 2.743 and once again you want to round it up to 3 significant figures, then once you will realize that up to 3 significant figures, the rounded up number will be written as 2.74. So, now the rules, if we formalize them, we will get the rules as, if the preceding digit is raised by 1, if the digit to be dropped is bigger than 5 and this is left unchanged, if the digit to be dropped is less than 5. So, we look at the digit which has to be dropped and we see if the digit to be dropped is bigger than 5, we raise the preceding digit by 1, and if it is less than 5, we leave it unchanged. But then the question comes, what happens if the digit is, if you have a number something like 2.745 and this you have to write up to 3 significant digits. So, if the digit to be dropped is 5, then there is an ambiguity. And here the convention which we use is that if the digit to be dropped is 5, then we look at the preceding digit. If the preceding digit is even, then we drop the 5. So, for example, when 2.745, because the digit to be dropped is 5, we look at the digit before this, it is 4. So, this is an even digit. So, we will drop the 5. So, this digit will become 2.74. And if the preceding digit is odd, then we add 1 to the preceding digit. For example, if we are talking of 2.735 up to 3 significant digits. We look at this digit 5 and the digit preceding to this is 3, which is odd. So, therefore, this would be rounded up as 2.74. But there is one more thing we keep in mind. If we have to round up a number like 2.7351 up to 3 significant digits, which means we have to retain the first 3 digits and the digits to be dropped are 5, 1. So, in this case, because what we are dropping is bigger than 5, because there is a 1 following that. So, this will be in that case written as 2.74, and this would even happen if we have something like 2.7451, and if we have to keep this up to 3 significant digits, so that means we are looking at 2.74, but now the part which we are dropping is bigger than half, because 5 is followed by a 1. So, in this case this will be written as 2.75. Now, let us take one example here which will help us to understand all these things. Let us say, suppose length of a rectangle is measured as 16.2 centimeters and the breadth is measured as 10.1 centimeters, and this is using a meter scale, and we want to find out the area. Now, if we were to use a calculator, we will work out a number, we will multiply these two, 16.2 into 10.1, and our answer will come out to be something like, I think, 163.62 centimeter square. So, but let us look at the concept of significant digits and errors, and so we will let us see how to write this correctly. So, if the length, since the last digit here is 0.2 centimeter, the last significant digit is there. So, the length we will write it as 16.2 plus minus 0.1 centimeters, and similarly the breadth will be written as 10.1 plus minus 0.1 centimeters. So, now when we multiply the two, we will get the area, and area will be equal to 16.2 plus minus 0.1 into 10.1 plus minus 0.1 centimeter square. So, let us see how to work this out. So, we can directly see this. If L is equal to 16.2 plus minus 0.1, then delta L is 0.1, and the relative error in length, which is delta L by L, this will be equal to 0.1 by 16.2, and this, if I express it as a percentage, this will be equal to 0.6%. Similarly, when I look at breadth, delta B upon B, this will be equal to 0.1 divided by 10.1 into 100%. So, this is equal to 1%, and area is equal to L times B, and if I write the error in area, delta A upon A is equal to delta L upon L plus delta B upon B, and I can also multiply both sides by 100, that will give me the percentage. So, what I will get is delta A upon A as a percent, this will be equal to 0.6% plus 1%. So, this is equal to 1.6%. So, delta A, the error in the area, this will be equal to 1.6 by 100 multiplied by the value of A, and A is equal to 16.2 into 10.1. So, therefore, what I get is area is equal to 163.62 centimeter square plus minus 1.6%. Now, this is where we will have to work out the total number of significant digits in the original quantities for each of them, for length as well as breadth were 3. So, the final answer when we express, we have to express it in the same number of significant digits, and this is the mistake which a lot of people make. So, therefore, here now when I express it to 3 significant digits, this will become 164 centimeter square. That means the last two, the decimal places will go away because we keep only the significant digits, and then to this I have to add 1.6%. Now, 1.6% of 163.62, this becomes equal to 2.6 centimeter square. But I have to, this 2.6 which I get, I have to keep it, I am adding it up to here to 164. So, I have to keep it as the same number of decimal places as 164. So, therefore, this 2.6 will be rounded up to 3 centimeter square, and so the final expression for the area will be 164 centimeter square plus minus 3 centimeter square. So, this is how one expresses the a quantity which is obtained by a product. Now, one thing which we will realize is if we look at relative error, this depends not only on the number of significant digits, but also on the number being measured. So, for example, when I look at mass being measured which is 1.02 grams and I measure it up to an accuracy of 0.01 grams, then the relative error here is 0.01 divided by 1.02 into 100, and this will be equal to 1%. Whereas, if the same relative error is there, if there is a mass of almost 10 grams, let us say 9.89 grams, which has also measured up to an accuracy of 0.01 grams, in this case the relative error you will realize will be much less. This will be equal to 0.01 divided by 9.89, and this, when I express it as a percent, this turns out to be equal to 0.1%. So, for the same least count, if the original mass was more, the relative error in that mass is much less as compared to a lighter body. Now, there is another rule which we use. If you have multiple step calculations, then what we do is, so this we should keep in mind when we have multiple step calculations, then in the intermediate steps we retain 1 extra digits to take care of errors which could creep in because of multiplication, divisions, etc. We keep 1 extra digit, and in the final answer we will follow the rules. So, when we write the final answer, we keep the number of significant digits as per the rules which we have defined, but in the intermediate steps we retain 1 extra digit. Thank you.